Hello, this is MATH1131 Calculus, and in the course of these videos I'm going to do selections of problems from various chapters just as an adjunct to your normal tutorials. One way of using these sensibly is to have a look at the question, have a look at the video, and then see, without taking notes, see if you can yourself write down good, correct solutions having seen the problem done. It's a good way of learning how to do mathematics. Get the ideas in your head firstly, watching the video, and then try sitting down and doing the problem again yourself. So I'm going to do question 6, which is really deriving a very nice thing called the arithmogeometric inequality. And I'll say a bit more about the geometry of that later as well. So we begin with something very simple. We're going to take this x minus y all squared, and we're just going to expand it. And we're going to observe then that x minus y all squared, whatever it is, it's going to be non-negative, because whenever you square a real number, you have to get a positive or zero number. So that is a true statement. And now when I expand it, I get x squared plus y squared minus 2xy bigger or equal to 0, and that gives me that x squared plus y squared is bigger or equal to 2xy. Is bigger or equal to 2xy. Now in particular, from this, I'm going to put a equal to x squared and b equal to y squared. So but a is x squared, b equals to y squared, and I'm going to take, so that means that a and b are squares, and so they're both positive. And when I substitute these in, I get the following. So I get a plus b, there, is bigger or equal to 2. Now if I want to get my a, remember a is positive, so x is going to be the square root of a. And from here, y is going to be the square root of b, and so when I multiply those together, I get 2ab. And traditionally what we do is we divide by 2 at this point, and write a plus b over 2 is bigger or equal to root ab. And that inequality is a very famous inequality. It's called the arithmogeometric inequality. There are generalizations of this, but that's all we need for this particular problem. Algebraically, it's saying that if you think of a plus b on 2, if you just think of two numbers and you add them and divide by 2, it gives you the average, sometimes called the arithmetic mean, or the average of the two numbers. If you take the square root of the product of two numbers, then that's called the geometric mean, which you may or may not have seen back at school, but it's called the geometric mean. And so what this says is that the arithmetic mean of two numbers, two positive numbers, exceeds, is bigger or equal to, the geometric mean of those two numbers. And so that solves, in fact, parts A and B of that question. So that was part A, was just to do that, and part B was to do that. It also asked you about equality. When are these equal to each other? When does that actually equal to that? Well, if you look back in the steps that we did here, they will be equal when these two numbers are equal. So we really have naught equals naught there. And that'll be when x is equal to y, and that means that a equals b. So we have equality. We have equality when a equals b. And you can check that if you do a plus a over 2 is a, and the square root of a times a is also equal to a. So you can check that that's in fact the case. Part C was simply to apply this to idea to find the minimum value of this function x squared plus 1 over x squared. And all I'm going to do is here, I'm going to just use this arithmogeometric inequality. I'll probably use that particular form of it back there. That is, I multiply the 2 back up the other side, and I'm going to think of that as my A, and that as my B. And applying this arithmogeometric inequality, this says that y is bigger or equal to twice the square root of that times that, so that's x squared times 1 over x squared, And these cancel, and so I just get 2. So that says y is bigger or equal to 2. Bit of a subtlety here. That doesn't mean that 2 is at the moment necessarily the minimum. It just says that y has to be at least as big as 2. So we have to check that y can actually take the value 2. And if we look back here, we see if I put x as 1 in both places here, and then I will get indeed y equals 2. So I need to say and y equals 2 when x equals 1, or if you will, minus 1. So we have a minimum. So y has a minimum of 2 at x equals, well, in fact, plus or minus 1. And you might like to think of what the graph of this looks like, to draw the graph of this without using too much calculus. It's got a minimum of 2 at plus or minus 1. As x gets very close to 0 this way, this number's getting small, but this number's getting very big. So this is going to zip up to infinity here. It turns here at that point 1, 2, and then it goes off. For x very large, that term is going to be very small, and so this is roughly a parabola. So this is getting close to, if you imagine the y equals x squared parabola coming through here, that's going to be getting closer and closer to that. And notice also it's an even function. If you replace x with minus x, then nothing happens. And so it's an even function, so you can copy it on the other side. And so the graph looks like that. And you might like to think of drawing in some kind of dotted asymptote here. This is getting closer and closer to, as I move this way, this is the line y equals x squared. So this blue curve, in fact, is the graph of this function, and we can see that it's got a minimum of 2 at x is plus or minus 1. That's the end of the problem, but I wanted to show you a little bit of some geometry that connects together with this lovely arithmogeometric inequality. So I'm going to start off with a line, segment A, and I'll call that line segment there AB of length A, and then I put my B there on a line. So I start off with just imagine a line there of length A and length B, and I'm going to draw a semicircle on that line. Now, how do we draw a semicircle? Well, we're going to take the average take the middle of this point. So if I call that point here E, take the middle of that, so AE equals to EC, and then I would draw a semicircle on that. So I'm going to mark in a diameter of this as well. So I'll go up to here. That's a diameter, a radius. I'm going to mark in a radius of this, and I'll call this point here F. Now we know what the radius is. The radius is going to be halfway along here. So EF is a radius, and that will occur in the middle between A and B, so that's going to be A plus B on 2. So let me just note for the moment that that radius of this circle is A plus B on 2, and that's looking very much like our A plus B on 2 in the arithmogeometric formula. Now, interesting question now to ask is, well, we know what that length is, but what's this one? This perpendicular here. So at the point B, I'm going to raise a perpendicular and see where it meets the circle. And I'm going to calculate that length x there. So this one here is a radius of the circle, and this one here is just some length x there. Okay, so the picture's probably getting a little bit complicated, but I'm going to draw some triangles in. So I'm going to join up this up to there and that down to there, and draw in two triangles here. Now if you look in those triangles, if that angle's there alpha, we know the angle in a semicircle is a right angle. So if this is alpha, then this angle over there is 90 minus alpha, and that's a right angle there, so that's alpha up in there. So a little bit of high school geometry, and we can see that that angle alpha equals that angle alpha. And so from that we can see that two similar triangles here. So we see that this triangle, ADB, is going to be similar to the triangle BDC, and because they have two pairs of angles. They've got a right angle and they've got the angle alpha the same. So that means I can write down that this length dB, that's x divided by the base, which is A, in this triangle. That's the side opposite the angle alpha, divided by the other side, the non-hypotenuse side. In this triangle, that's going to be equal to B divided by that side, which is x. And if I cross multiply, I get x squared is AB, and that says x is equal to the square root of AB. Because that number was the same as we saw on the other side of our arithmogeometric inequality. And we can see in the picture that this length EF, this radius, is always bigger or equal to this chord here, BD, and that's exactly our arithmogeometric inequality. Because EF, remember, was A plus B on 2, and that has to be bigger or equal to root AB. So there's a little geometric proof of the arithmogeometric inequality. Moreover, we see that when we have equality, well, if this point B was actually at E, then that length would equal that length. And if B is at E, then this would be midway between them, and B and A would have the same length. And so we can see again, we have equality from the geometry, we have equality when A equals B. So that's a little sidelight extra piece related to this problem.